Hello everyone. Today we will cover advanced topics in generics. We have already covered some basic concepts in generics, so let's quickly summarize why we use generics in our code. The answer comes down to three major benefits: reliability, readability, and reusability. First, generics improve reliability through compile time error detection. They act as a safety net by preventing type-related errors before the program actually runs. Second, generics improve readability because they make the allowed data type clear. When we see a generic type such as ArrayList string, we immediately know that this list is designed to store string values. Third, generics improve reusability. They allow us to create classes, interfaces, and methods that can work with different data types instead of being limited to only one specific type. So, if we want to summarize what generics allow us to define a class, interface, or method once, and reuse that same code with many different data types while still maintaining strong type safety. When you declare a variable in Java, you can think of it as having three parts: type, name, and value. The type is like the box manual. It answers two important questions: what kind of box is it, and what's allowed inside this box? The name, as the term suggests, is like a name tag on the box. It answers the question, what do we call this box, so we can refer to it in our program. Now let's look at an example. First, int tells Java that you are using a primitive type, meaning only integer or whole number values are allowed in this box called x. For primitive types, the size of the box is fixed, in this case 32 bits or 4 bytes. Also, the value is stored directly inside the box, so here the value 71 is placed directly into x. Putting it all together, this one line tells Java, create a box that can only hold whole numbers, name it x, and store the value 71 directly inside it. Next, string with square brackets tells Java that you are using an array, which is a reference type, and only string or text values are allowed in this box called car. An array is like a fixed size cargo container that has many boxes, 100 boxes in this example. Note that this is not a primitive type, so it works differently. Each box does not store the actual text data directly. Instead, it holds a reference, a memory address, to a string stored elsewhere in memory on the heap. So instead of placing the actual data directly on the right side, you use the new keyword with the box type, such as string, followed by square brackets to specify the size, telling Java to create an array and allocate space for its elements in memory. So this basically tells Java, create an array with 100 elements, name it car, and make sure each element can only reference a string. Next is a generic type. Here, ArrayList string tells Java that you are using a reference type list, and only string or text values are allowed in this box called book. An ArrayList is like a flexible container. Unlike an array, it can grow and shrink dynamically. The string inside the angle brackets is the key part. It tells Java that every element in this list must be a string. Each position in the list does not store the actual text directly. Instead, it holds a reference, memory address, to a string stored elsewhere in memory on the heap. So you use the new keyword with a container type like ArrayList in this case, followed by angle brackets and parentheses. This tells Java to call the constructor and create space for the object in memory. Putting it all together, create a flexible list, ArrayList, name it book, and make sure each element can only point to a string. If you want to use different data types for different positions in a generic class, you can place multiple types inside the angle brackets, with each one corresponding to its own position. In Java generics, these types act as placeholders that are replaced with actual data types later when the code is used. For example, when you see box T, it means there is one position that will be filled with a specific type later, such as string or integer. When you see something like fly T1, T2, it means there are two separate positions and each can hold a different type. The same idea applies to methods as well. When a method is written as t void print tparam, it introduces its own type placeholder, and the actual type is determined at the moment method is called. You can see this clearly in real examples. An ArrayList string is designed to store only string values. A hashmap string integer uses two positions, where the first type represents the key and the second represents the value. A linked list double is restricted to storing only double values. Overall, the angle brackets define type positions, and the actual types are supplied later, allowing the same code to be reused safely with different data types. Let's look at an actual code example. The pair class is a generic class, which means it is defined with a type parameter t. This type t represents a placeholder for a real data type that will be specified later when an object is created. Inside the class, there are two variables, var1 and var2, and both are declared using the same type t. This means the class is designed to store two values of the same type, whatever that type may be. When the constructor is called, it receives two inputs, both of type t, and uses them to initialize the variables var1 and var2. At that moment, t is no longer just a placeholder. It becomes a concrete type, such as string, integer, or any other object type, depending on how the pair object is created. As a result, both variables are guaranteed to be of the same consistent type within that object, ensuring type safety while still keeping the class flexible and reusable. Next, there are two different methods. The first method, MT, is a regular method that uses the class-level generic type t as its parameter. The second method, MS, is a generic method because it declares its own type parameter s with angle brackets after the public access modifier and before the return type. It is important to understand the difference between the two. The regular method MT uses the class-level generic type t, which is determined when the object is created. That means the method is restricted to the same type as the object, just like the var1 and var2 variables. On the other hand, the generic method MS declares the generic type S with angle brackets in its signature, which allows the method to introduce a new type each time it is called. The type S is determined at the moment of the method call based on the argument passed in. This means the method can accept different types regardless of the class-level generic type across different calls, making it more flexible. Now let's instantiate it to see how it works. We create an object P. At this moment, the generic type T is fixed as string. That means everything in the class that uses T will now work strictly with string. So var1 and var2 now hold apple and banana respectively. Next, we call the method MT, which uses the class-level type parameter t. At this point, t is already fixed as string because we treated the object as pair string. Therefore, MT can accept cherry because it is also a string and it stores that value in var3. So the output will be apple and banana : cherry. However, p.mtl100 causes an error. Here, 100 is an integer literal, a primitive int, and Java can autobox it to an integer wrapper class, but that still does not match string. Since t is fixed as string, the method only accepts string, so this call is invalid. Next, we call the generic method ms, which has its own type parameter s. Unlike t, which is already fixed as string, the type s is determined at the moment of each method call based on the argument passed in. When you pass cherry, you are passing a string, so s becomes string. When you pass 100, you are passing an integer literal, primitive int, which Java autoboxes to integer, so s becomes integer. When you pass 3.14, you're passing a floating point literal, primitive double, which Java autoboxes to double, so s becomes double. Because ms defines its own type parameter s, it is not restricted by the class level type t. This means the method can accept different types each time it is called. Therefore, all three calls are valid even though the object was created with t fixed as string. In summary, a regular method that uses a class-level type parameter is tied to the class or object's type and enforces consistency once it is determined at instantiation, while a generic method defines its own type at the method level when it is called and allows more flexible usage. Let's look at a very practical application. Sometimes you want a method to work with numeric data only, such as integer, double, or long, and you want to prevent incompatible types like string, boolean, or other non-numeric objects from being used. You also want to catch errors at compile time when an incompatible data type is used, rather than discovering them later at runtime. Take a look at the class hierarchy diagram before we dive in. The number class includes all numeric types, such as wrapper classes like integer and double, as well as big integer and big decimal. On the other hand, string and other non-numeric types do not belong to the number class. They are part of separate branches under object. We can take advantage of this hierarchy by setting a boundary. If we set the upper bound to number, then only types within the number hierarchy are allowed, while non-numeric types like string are excluded. This is exactly where bounded generics become useful, especially upper bounded generic types in this case. This notation means that the type n is restricted to the number class or any of its subclasses, setting number as the upper bound within this hierarchy. Now you can clearly see what extends number means in a generic method. It sets an upper bound which restricts the method to accept only types that belong to the number hierarchy. That is why arrays of integer, double, and long work without any issue, because all of these classes extend number. On the other hand, string does not belong to this hierarchy. It is a separate branch under object, so the compiler rejects it before the program even runs. This is the key advantage of bounded generics. They enforce type safety at compile time by allowing only compatible types and preventing invalid ones from being used. Are there any lower bounds? Yes, there are. A lower bound is defined using the super keyword with a wildcard. While an upper bound restricts a type to a class and its subclasses, a lower bound allows a type to be that class or any of its superclasses in the inheritance hierarchy. So this notation means the type can be integer, number, or object. Think about why we need this. Sometimes your goal is to add a specific type safely, such as integer. Types like double or float are rejected because they are not supertypes of integer. They are sibling classes in the hierarchy. This safety is enforced at compile time, which is much easier and cheaper to fix than handling errors later at runtime using if statements or exception handling. Now we are ready to dive into actual lower bounded generic code. The method stackbox takes an array list as input, but the array list type is lower bounded to integer. This means the method is allowed to add integer values safely, regardless of whether the actual list is an array list integer, array list number, or array list object. We can create an array list double or array list float, but we cannot pass it into stackbox because double and float are not supertypes of integer. They are sibling classes under number. So we can run the stackbox method with an array list integer, array list number, or array list object, but not with an array list double or array list float. The key point is that the lower bound guarantees safe insertion inside the method, not that the list will only contain integers forever.